We've landed rovers on Mars, some designed for missions of only 90 days that ended up operating for over a decade. We've flown helicopters through its thin air, an engineering achievement many aerospace experts doubted was even possible before it actually happened in 2021. We've mapped its canyons, drilled its rocks, and listened to its wind through a microphone 140 million miles away. Recordings that let people on Earth hear, for the first time in history, what another planet's atmosphere actually sounds like. Machines have been visiting Mars regularly since the 1970s, and NASA currently operates multiple active spacecraft there simultaneously, from orbiters mapping the planet's geology to rovers crawling across its surface searching for signs of ancient life. And yet, more than half a century later, not a single human being has ever set foot on it, or even left low Earth orbit farther than the Moon. That gap is worth sitting with, because it isn't a story about a lack of ambition or a lack of trying. We can build a nuclear-powered laboratory the size of a car, and land it gently on another planet using a hovering sky crane, a feat that sounded like science fiction when it was first proposed. We can fly a helicopter in an atmosphere 1% as thick as our own. What we cannot yet do, what nobody on Earth has yet solved despite decades of trying and billions upon billions of dollars spent, is keep a human being alive long enough, protected enough, and sane enough to make the trip there, walk around, and come home again safely. This is the real story of why Mars has stayed just out of reach for humans, even as our machines have thrived there for decades, generation after generation of increasingly capable robotic explorers. Not because it's truly impossible in the sense of defying physics, but because the honest list of what stands in the way is longer, stranger, and more unforgiving than most people realize. The first problem with Mars is simply how far away it is, and how badly that distance breaks the intuitions most people carry from watching the moon landings. Apollo astronauts reached the moon in about 3 days, covering roughly 240,000 miles of open space using guidance computers less powerful than a modern pocket calculator. Mars, at its closest approach, is still around 140 times farther away than the moon ever was for Apollo. And because Earth and Mars orbit the sun at different speeds, on different sized orbits, you can't just point a rocket at wherever Mars happens to be right now and go. Spacecraft have to launch along a curved trajectory that intercepts where Mars will actually be by the time they arrive, months later, and the two planets only align well enough for an efficient transfer once every roughly 26 months, when their relative positions create what's called a launch window. Miss that window, and the next real opportunity is more than 2 years away, with the crew and hardware simply waiting on the ground in the meantime. Even with the launch timed perfectly, the trip itself takes 6 to 9 months one way, using conventional chemical propulsion, the same basic rocket technology that got Apollo to the moon, just used over a vastly longer distance. That means a round-trip mission, including time spent waiting on the Martian surface for the planets to realign for the return journey, stretches out to somewhere between 2 and 3 years, door to door. For comparison, the longest continuous stay on the International Space Station, humanity's most extensive experience with long-duration spaceflight, is a little over a year, set by astronaut Frank Rubio during an extended mission caused by an unplanned spacecraft issue. A Mars mission would roughly double or triple even that record, in a vehicle with none of the resupply flights, rapid abort options, or nearly instantaneous communication that the space station enjoys every single day. Some researchers are working to shrink that transit time. A 2025 study published in Scientific Reports outlined trajectories using SpaceX's Starship that could theoretically cut the one-way trip to as little as 90 to 104 days, using more fuel-intensive paths that trade propellant efficiency for speed, since a faster trip directly reduces how long a crew spends exposed to deep space radiation. Even if that approach works exactly as modeled, it doesn't eliminate the underlying problem. It only makes it somewhat more survivable. And every one of those faster trajectories still depends on propulsion technology and in-space refueling systems that, as of 2026, have not yet been fully demonstrated in practice anywhere by anyone. Distance alone would be a solvable engineering problem if it weren't for what that distance actually exposes a human body to along the way. This is, according to nearly every space agency studying the question, the single hardest unsolved piece of sending humans to Mars: radiation. On Earth, we're protected by 2 enormous, largely invisible shields: our planet's magnetic field, which deflects most charged particles from the sun and deep space, and our atmosphere, which absorbs most of what gets through the magnetic field anyway. Astronauts on the International Space Station still benefit from most of that protection, since the station orbits well within Earth's magnetosphere, at an altitude of only about 250 miles. A crew traveling to Mars would leave both shields behind entirely for the better part of a year at a stretch, spending months exposed directly to 2 dangerous sources of radiation: galactic cosmic rays, high-energy particles originating from outside our solar system that are extremely difficult to shield against because of how much energy they carry, and solar energetic particles, sudden bursts of radiation from the sun itself that can spike to dangerous levels with relatively little advance warning, sometimes only hours. NASA has set a career radiation exposure limit for its astronauts of 600 millisieverts, based on research into acceptable long-term cancer risk, with the exact figure varying somewhat by age and sex, since younger astronauts face a longer remaining lifetime for radiation-induced effects to develop. Multiple independent studies modeling a full Mars mission, factoring in the transit time, the surface stay, and the return trip, have found that astronauts using conventional trajectories would likely absorb somewhere between 600 and 1,000 millisieverts of radiation over the full mission, depending heavily on solar activity at the time and the specific trajectory used. That means a single Mars mission, using anything close to today's technology, could use up an astronaut's entire career radiation allowance in one trip, or exceed it outright, permanently disqualifying that astronaut from ever flying in space again, even if they wanted to. Research modeling exposure to the spine's bone marrow, a tissue especially important for blood cell production, has found that on a roughly 1,000-day mission, doses to certain organs could reach as high as 4 sieverts, into a range comparable to what's seen in nuclear accident survivors or radiotherapy patients, according to researchers who have specifically studied both. The faster 90 to 104-day trajectories being explored specifically to cut this risk still bring total doses down to only around 357 millisieverts by some estimates, a real improvement, but still a substantial fraction of a career's worth of exposure spent on a single journey before any surface exposure on Mars itself is even factored in. Shielding is the obvious answer, and it's also where the engineering runs into a wall. Effective radiation shielding requires mass, thick layers of water, polyethylene, or metal, arranged densely enough to actually stop high-energy particles rather than just slow them down. And mass is the single most expensive thing to launch into space, since every additional kilogram requires proportionally more fuel just to lift it off Earth in the first place. Every additional kilogram of shielding is a kilogram of fuel, food, or equipment that has to be left behind, or an entirely larger, more expensive rocket that has to be built to carry it in the first place. Some proposals suggest using the ship's own water and waste storage as a radiation buffer around a small, heavily shielded shelter for crew to retreat to, specifically during solar storms, but nobody has built and flight tested a system like this for a mission anywhere close to Mars, distances where the storm warning time is far shorter than what Earth orbit satellites currently provide. On the Martian surface itself, the situation is only marginally better. Mars has no global magnetic field and only about 1% of Earth's atmospheric density, meaning surface radiation levels remain far higher than on Earth. Most serious habitat proposals involve burying structures under several meters of Martian regolith, or building inside lava tubes, specifically to get enough shielding mass overhead to make long-term surface habitation survivable. Surviving the trip is only half the problem. Actually, landing safely on Mars is its own entirely separate engineering nightmare, one serious enough that NASA has an official nickname for it: 7 minutes of terror. Mars presents a landing problem that doesn't exist on the Moon or on Earth, because it sits in an unfortunate middle ground between the two. Its atmosphere is thick enough to generate serious heat and drag during entry, meaning a spacecraft needs a heat shield just like it would returning to Earth, and just like the moon landing missions never needed at all. But that same atmosphere is only about 1% as dense as Earth's, which means it's nowhere near thick enough to slow a heavy spacecraft down using parachutes alone, the way capsules do when returning to Earth's much thicker air. Every robotic mission that has ever landed successfully on Mars has had to thread this needle using some combination of heat shields, supersonic parachutes, and retro rockets fired at exactly the right moment, all executed entirely autonomously, because the communication delay between Earth and Mars, anywhere from about 4 to 24 minutes one way, depending on the planet's relative positions in their orbits, makes real-time human control from Earth physically impossible. By the time a warning signal reaches mission control, the spacecraft has already either landed safely or been destroyed, with no possibility of any human intervention in between. Rob Manning, chief engineer at NASA's Jet Propulsion Laboratory, who has led entry, descent, and landing on several robotic Mars missions, has described one of the specific physics problems this way. Firing engines backward while moving through an atmosphere generates a shock front that can move around unpredictably and strike the vehicle, potentially destroying it. According to Manning, this effect turned out to be extremely difficult to model in advance because there was virtually no prior flight experience firing rocket engines directly into a high-speed oncoming airflow before engineers actually had to solve it for real missions. It's worth noting that SpaceX's own practice of landing Falcon 9 boosters by firing engines backward at supersonic speeds through Earth's atmosphere has, according to Manning, actually generated genuinely useful data for understanding this exact problem, even though those landings happen in Earth's much thicker atmosphere rather than Mars's thin one, meaning the physics don't translate perfectly, but do provide a real, flight-tested starting point. Every robotic mission NASA has successfully landed on Mars to date has weighed at most about 1 metric ton, roughly the mass of a small car, A crewed mission would need to land a habitat, life support systems, months or years of supplies, and the return vehicle itself altogether. Payloads plausibly weighing 20 metric tons or more per landing, over 20 times heavier than anything successfully landed on Mars so far, and likely requiring multiple separate landings, coordinated precisely enough that the crew can actually reach everything they need once on the surface. No entry, descent, and landing system capable of safely putting that much mass on the Martian surface has ever been demonstrated by any space agency or company anywhere. SpaceX's Starship program is specifically being developed with this problem in mind, using its own engines for a fully propulsive landing rather than parachutes, relying on the vehicle's own thrust to slow it from orbital velocity all the way down to a gentle touchdown. But as of 2026, Starship has completed a series of suborbital test flights launched from Texas, splashing down in the ocean rather than landing on solid ground. It has not yet demonstrated an orbital Mars-relevant landing, let alone landed anything on Mars itself, and recent test flights have continued to show real reliability problems, including engines failing to relight during booster landing attempts. Assuming a crew survives the trip and the landing, the next problem is simply staying alive on a planet that offers almost nothing a human body needs to survive on its own. Mars's atmosphere is roughly 95% carbon dioxide. At a pressure so low, less than 1% of Earth's sea level pressure, that exposed liquid water would boil away almost instantly even at freezing temperatures. A strange consequence of how pressure and boiling point interact at that extreme. There is no breathable air, no protection from ultraviolet radiation since Mars lacks an ozone layer, and average surface temperatures well below freezing, with wide daily swings that can range from a relatively mild afternoon to brutally cold nights within the same 24-hour period. Every single thing a human being needs to survive, oxygen, drinkable water, breathable air pressure, food, and a stable temperature, has to either be brought from Earth or manufactured on site, and has to keep working continuously for months or years, without the kind of regular resupply missions that keep the International Space Station running smoothly today. This is why both NASA and SpaceX have increasingly focused on something called in situ resource utilization, or ISRU, using Mars's own local materials rather than hauling everything needed for survival across 140 million miles of space. NASA's MOXIE experiment, flown to Mars aboard the Perseverance rover and about the size of a small toaster, successfully demonstrated a small-scale technology for converting Martian atmospheric carbon dioxide into breathable oxygen, running multiple successful test cycles, and proving the basic underlying chemistry works reliably in actual Martian conditions, rather than just in an Earth-based laboratory simulation. Scaling that process up by orders of magnitude, enough to produce sufficient oxygen and fuel to support a crew for years and launch a return vehicle back off the surface, reliably, continuously, in an environment no human has ever tested large industrial equipment in before, remains a substantial unproven step beyond a small toaster-sized demonstration unit that ran for a limited number of cycles. Every one of these systems, oxygen generation, water recycling, temperature control, food production, also has to work with essentially no margin for error and no possibility of a quick resupply flight if something breaks down partway through the mission. On the International Space Station, a life support failure can often be addressed with parts flown up on the next supply mission, typically within weeks, sometimes even days in an emergency. On Mars, the next supply mission might be more than 2 years away, arriving only during the next favorable launch window when the planets happen to realign. A serious life support failure on Mars isn't a problem to be patched with an emergency delivery. It's potentially the end of the mission and the crew, with no realistic possibility of rescue arriving in time. What months of isolation actually do to people? Even if every piece of hardware works exactly as designed, there's a category of Mars mission risk that no amount of engineering alone can fully solve, because it isn't a hardware problem at all. What months of extreme isolation, confinement, and distance actually does to the human mind. The Planetary Society, drawing on decades of astronaut research and direct interviews with veterans of long-duration missions, has been direct about this challenge. Even NASA's most rigorously screened, highly trained, mission-focused astronauts experience periods of depression, loss of motivation, and interpersonal conflict during long-duration missions, despite being selected specifically for their psychological resilience and their demonstrated ability to work through exactly these kinds of problems. Researchers have documented something informally called the space stupids, a perceived decline in concentration and task performance during extended spaceflight that, curiously, standard cognitive testing often fails to fully capture, even though the astronauts experiencing it report it as very real and noticeable in their day-to-day work. On a Mars mission, these effects would need to be endured for 2 to 3 years, far beyond the roughly 6-month to 1-year missions that represent the outer edge of humanity's current experience with long-duration spaceflight. and without the psychological safety net that even ISS astronauts have, the ability to see Earth out the window as a small, reassuring blue marble, and to talk to family and mission control in near real time whenever something feels difficult. That last point matters more than it might seem. Once a crew is more than a few light minutes from Earth, ordinary back-and-forth conversation becomes physically impossible, no matter how good the equipment is. At Mars's average distance, radio signals take anywhere from about 4 to 24 minutes to travel one way, meaning a single question and answer exchange with mission control could take the better part of an hour once both the question and the reply have made the round trip. For most of a Mars mission, real-time conversation with anyone on Earth, including family, spouses, or children back home, simply won't exist as an option. Every communication becomes a recorded message, sent and waited on, with no way to interrupt, clarify, or respond quickly if something is urgent or upsetting. The Planetary Society's assessment of this combined psychological and physical burden was blunt. Given the right rocket and spacecraft, a crew could probably survive a Mars mission and return home to tell the story, but performing a genuinely productive, rigorous program of scientific exploration once they arrived, worthy of the sacrifice it took to get them there, is, in their words, almost certainly not something today's technology and readiness level could support. The body itself starts working against you. Layered on top of the psychological toll is a well-documented physical one. Human bodies did not evolve for weightlessness, and every month spent in microgravity actively works against the systems that keep us functional on a planet with gravity, in ways researchers have been carefully cataloging since the earliest long-duration space flights of the 1970s and 1980s. NASA's Human Research Program has formally identified 5 major hazard categories and 32 specific risks associated with human spaceflight. And long-duration missions like a Mars trip would activate nearly all of them simultaneously, compounding on top of one another over years rather than months. Astronauts lose bone density and muscle mass continuously while in microgravity, even with rigorous daily exercise. Regimens involving specialized resistance equipment designed specifically to slow the process as much as possible. Vision changes are common on long-duration missions, believed to be linked to fluid shifting toward the head in the absence of gravity's usual downward pull, and the exact long-term consequences, including whether some of these changes are fully reversible after return to Earth, are still being actively studied by researchers today. All of this would need to be managed not just during the 6 to 9 month outbound trip, but throughout an extended stay on Mars's surface, where gravity is only about 38% of Earth's, enough to change how the body adapts compared to full weightlessness, but not enough to prevent the deconditioning that starts the moment a crew leaves Earth orbit and continues, in a different form, for the entire surface stay. And then, after months or years of that partial gravity adaptation, the crew would need to survive another 6 to 9 month trip home, arriving back on Earth's full gravity in bodies that have spent years adjusting to something else entirely, likely requiring extensive rehabilitation before anything resembling normal function returns. Some researchers have raised an even more unsettling long-term question: whether astronauts who spend extended periods on Mars might eventually become physiologically unable to safely readapt to Earth's gravity at all, a possibility that remains genuinely unresolved because nobody has ever kept a human being in a reduced gravity environment for anywhere close to the length of time a real Mars mission would actually require. The longest any human has spent continuously in microgravity is still measured in months, not years, which means the physiological data needed to fully answer this question simply doesn't exist yet, and won't exist until someone actually attempts a mission of this length. The cost problem. Underneath every other problem, running quietly underneath every technical challenge described so far, is a much less glamorous one: money and the sheer scale of investment required to solve all of these problems simultaneously, on a timeline anyone actually wants to see happen in their own lifetime. $15 billion in private investment into Starship development alone represents one of the largest privately funded engineering efforts in human history, and that figure covers only the rocket and its supporting infrastructure, not the habitats, life support systems, spacesuits, surface vehicles, and years of consumables a genuine Mars mission would additionally require, all of which have their own separate, largely unsolved cost and engineering challenges. Government space agencies face their own version of this problem, spread across multi-decade budget cycles that have to survive changes in political leadership, shifting national priorities, and competition for funding against every other government program. NASA's own Artemis program, intended partly as preparation for Mars, has already run years behind its original schedule and well over its original budget, illustrating just how difficult it is to keep even a moon-focused program on track, let alone one aimed at a destination that takes years rather than days to reach. Every dollar spent solving one piece of the Mars puzzle, radiation shielding, life support reliability, propulsion, landing systems, is a dollar not spent on another piece, and no single organization, public or private, has yet demonstrated it can fund and execute all of these simultaneously on a schedule that holds up against reality rather than optimistic projection. None of this means humans will never reach Mars. Every single challenge described here is, in principle, solvable. None of it violates the laws of physics, and serious engineering work is actively underway on nearly every problem listed, spread across multiple space agencies and private companies working the problem from different angles simultaneously. NASA continues refining its Artemis program, treating a return to the moon partly as a test bed for the life support, radiation shielding, and long-duration mission techniques a Mars trip would eventually need, on a scale close enough to home that mistakes are recoverable in ways they wouldn't be at Mars distances. SpaceX has poured more than $15 billion into Starship development specifically with Mars in mind, and has spent 2025 and 2026 running an ongoing series of test flights working through the vehicle's basic reliability, even as recent tests have shown just how much remains unresolved, including repeated engine failures during relight attempts and a landing so gentle in one case that the booster remained floating, intact, in the ocean for days afterward as a genuine engineering curiosity rather than the planned disposal outcome. But it's worth being honest about the gap between public timelines and actual technical readiness. Elon Musk has repeatedly projected crewed Mars missions on timelines that have consistently slipped by years each time they've been revisited. A 2016 target of 2024 became a 2020 target of 2026, which has since shifted toward the early 2030s in most current projections, contingent on cargo missions, first proving out landing and resource utilization technology that hasn't yet been demonstrated even once, anywhere, by any organization, public or private. As of the most recent Starship test flights in July 2026, the vehicle has not yet demonstrated orbital refueling, a full Mars-relevant entry and landing sequence, or any of the radiation shielding and life support systems a crewed mission would actually require to keep a human being alive for years at a stretch, far from any possibility of rescue. An ESA scientist, reviewing the current state of Mars mission planning, has gone so far as to call the radiation problem alone a potential showstopper. If it isn't meaningfully solved before any crewed mission is seriously attempted, regardless of how far along the propulsion and landing technology has progressed by that point in the process. Every one of these separate research efforts and technology programs, NASA's Human Research Program, ESA's radiation modeling, MOXIE's oxygen generation demonstration, the Planetary Society's psychological assessments, SpaceX's ongoing Starship test campaign, and the various university studies on transit time trajectories, has approached this problem from a different angle, funded by different sources, staffed by different teams, and yet every single one has arrived at some version of the same conclusion. The individual pieces are each solvable, but assembling all of them into one working, reliable system on a timeline that survives contact with real budgets and real engineering setbacks remains the actual barrier standing between humanity and a footprint on Mars. That's the honest state of things in 2026, not impossible, in the sense that nothing here defies physics, but not remotely close to solved either. Every problem described in this video, the distance, the radiation, the landing, the isolation, the physiology, the resource utilization, and the sheer cost of funding it all at once, has to be solved simultaneously by the same mission, using hardware that has to work perfectly for years at a stretch, with no possibility of a quick rescue if any single piece fails partway through. Machines have been doing versions of this successfully since the 1970s, because a rover that breaks down simply stops working, sits quietly on the surface and waits for a successor mission someday, decades later if necessary, with no loss of life and no urgency beyond scientific disappointment. A human crew that experiences an equivalent failure doesn't get that option, and that single difference is, at its core, the entire reason Mars has remained a destination for robots rather than people for more than half a century of active exploration. If this is the kind of story that makes you want to understand what it will actually take to get humans to Mars, subscribe and turn on notifications. Because every single one of these challenges, distance, radiation, landing, isolation, physiology, resource utilization, and cost, is currently being worked on by real engineers at real space agencies and real companies in real time. And the gap between where we are now and where a crewed Mars mission actually needs to be is narrowing every year, even if it's narrowing more slowly than the headlines usually suggest.